Hello, physics students. It's Wednesday before Thanksgiving. I've had a couple of questions about the most recent assignment, that is the particle interaction assignment. So I thought I would make a recording of one more example of how to fill in the Feynman diagrams for particle physics. So of course you access the particle interaction assignment through Canvas. You wouldn't be watching this video if you weren't in Canvas though. And I am preferring the PowerPoint version of the assignment. So clicking here will allow you to download a PowerPoint that looks like the following. Oh shoot, I may have lost my PowerPoint. Oh, here. Ooh. Try this. Here's the PowerPoint assignment that you would download in PowerPoint form. The first 3 pages or 3 slides are not the assignment, but intro and resources. So here is the reference sheet that gives you the symbols and the charge of each of the particles of the standard model. The next slide is the diagram shapes for the Feynman diagrams. And then the final 4 slides are the 4 Feynman diagrams you need to fill in or complete. They're partially completed. So in class, I've given you pretty much diagram 2 as an example. So I would refer you to Tuesday's Zoom recording for help with diagram 2. Let's have a look at a slightly different diagram. Let's go for diagram 3 for another example. So reading the Feynman diagram for diagram 3, reading left to right, I see a muon and a muon neutrino interacting, right? There's 2 straight lines. They should actually have little arrows, but they're missing. I know that that's a muon and a muon neutrino based on the diagram. The muon and muon neutrino contact each other and interact with a force particle. And the force particle here is indicated by a dashed line. So I'm going to need to look up that particle to know which one it is. And then that force particle in turn becomes one of the options given on the right. So an anti-up or anti-charm quark plus either a down strange or bottom quark. British physicists call it a beauty quark. And these Feynman diagrams were created by a British institution. So our first step is we basically go left to right. So our first step is to find the charge of the muon and the muon neutrino from the reference sheet. So a muon is a lepton. The muon is the fat cousin of the electron. So here's the muon with that goofy U letter, Greek letter mu. And I can see in the chart that the charge of the muon is -1. So I can add that to my diagram. And -1 should be over here. I can just drag it over. You can also fill it in on your own in handwriting or whatever. And then the muon neutrino, again, back to the reference sheet. Muon neutrino is a kind of a sidekick of a muon that is emitted in weak nuclear interactions. And the charge of the muon neutrino is 0. So a lot of these Feynman diagrams are interactions of particles and antiparticles, but in this case, we have a muon interacting with its neutrino. So I have here a net charge before the interaction of -1. So the next step is to find out what this dotted line symbol means and figure out if I can get a charge corresponding to this force particle indicated by the dotted line symbol that's equal to -1. So to the particle shapes page, I see that the dotted line indicates either a W plus, a W minus, or a Z boson. And of course, W plus, W minus, and Z bosons have to do with the weak nuclear force. So it makes sense that this is involved in a muon plus muon neutrino. So I have 3 options here, W plus, W minus, or Z. And I have to figure out if one of these 3 carries a -1 total charge so that I am conserving charge in this interaction. So I go back to my reference page Now I'm looking at the exchange bosons up here in the top right. Here's the W plus. It has a charge of +1. That's not going to work. Here's W minus. It has a charge of -1. So that does work. Z has a charge of 0. So that does not work. So this interaction particle, this intermediate particle, by kind of deduction, must be the W minus boson because it's the only one that has a charge of -1. So if I have to have charge conserved, then I must choose the W minus boson for this interaction. Oops, somehow I got that sideways, so I just didn't give enough room. So you can write the symbol W minus, you can write out W and the word minus, either is fine. Okay, so I'm 2/3 of the way through. I have a particle interaction that is muon plus muon neutrino, net charge of -1, transforming into a W minus boson, net charge, total charge of -1. Now I need to see if I can come up with a pair of particles that the W minus transforms into that also has a net charge of -1. And so I just picked 2. So let's go for just the top one here, anti-up and, I don't know, strange. Let's see if that works. So I just indicated which ones I'm caring about, right? I can't really erase the other ones here. So now I need to go back to the reference sheet and find out what the charge of anti-up is, oops, and what the charge of strange is. So anti-up, so these are the quarks. Here are the anti-quarks. Here's anti-up, the U with the bar indicating anti-up, and its charge is -2/3. So I go back to my diagram and enter that for anti-up. Then I need to know what the charge of, or finally, I need to know what the charge of the strange quark is. Again, back to my reference sheet. The strange quark, where is strange? Here's strange. S for strange has a charge of -1/3. So my last entry here for strange is -1/3. And I check to make sure that charge is conserved, my last step. Before the interaction, I have a charge of -1. Within the interaction, forced particle, I have a charge of -1. And the result of the interaction, -2/3 plus -1/3 is -1. So this is a valid Feynman diagram for a possible interaction of muon plus muon neutrinos. I hope that this additional example helps. And please keep emailing me if you have further questions.